So we're gonna go ahead and start. I don't know if do people appreciate the intros at the beginning, or is that just too awkward for?
I like it, but
okay. Why don't we do the short version, which is be snappy. Limit yourself to 5 seconds, 10 seconds. So I'm Craig Ogg. Organizer of this meetup, and I'm the CTO and general manager for community business here at Good. So I run product, technology, and community management, and we'll do it clockwise. Would you like to introduce yourself?
I'm Aaron. I work architect here at Good, working on making things faster and break less.
Hi, I'm TV. I'm talking today, so that's my name over there. Lately, my project has been this guy. So if you go to basil.org, you will find all the nice things about it. I'll talk about that in a month or two. But that's an interesting distributed file system for weekly connected offline things. That's my project right now.
My name is John Mitchell. I'm a super heavy Python server Django guy. I'm doing teaching and consulting.
My name is Ross Edwards. I'm co-founder of a data company focusing on the entertainment space.
I'm Anand Bolangadi. I work for a financial company. We develop a Ruby on Rails app for the company to originate loans and etc.
Camera guy? Or, yeah.
Okay, my name's Nathan. I'd like to spend more time writing Go and less time fixing other people's computers.
Good looking, man.
My name is Ryan. I know nothing about Go. I haven't seen it. I haven't touched any of it. I write Rails app myself, so I'm here to see what it's all about.
Bridger, I'm working on an iPad app. It's like a collaboration environment and a way to learn with people. And we have a Go server, so here to network.
I'm Brian. I work at Max CDN, and I've been trying to convince everyone at my work to write and Go for about a year now.
I'm Jacob. I started writing Go when it came out, just for fun. I never really wrote anything big with it, so I kind of like to see it done.
My name's Lars Letnin. I am one of the organizers of LA DevOps, and I consult here in LA.
Alright. Let's get going. So, today's topic is Go Nuts and Bolts. Go Nuts is the name of the mailing list, well, it's Golang Nuts. Go Nuts is the IRC channel. Nuts and Bolts. Bolt is a database. It's a key value flow. That's not relevant for you guys. It's relevant later. It's on GitHub under BoltDb. The primary author of it is Ben Johnson. So it's like not my project. I've just been involved in it for a while now, and I greatly enjoy using it. And I think it's like in this space right now the most present, most Go-like thing you can use. So what is it? It's a key value store. So you have a key, it has a value. There is nothing beyond that. There are no joins, no foreign keys, no structured data for them. You put in it. It's a byte slice. So, you know, if you want structure, you can have structure. You could, for example, store JSON in it if you wanted to, but it wouldn't do anything about the contents of the JSON. So this is kind of what it looks like to use. These are slices of an actual program. You open a database, and it might give you an error. You close the database. You can do put this key, this value, check for errors. You can get a key, and it will give you the value or a nil if it was not found. So all of this is byte slices going in and out. It's your responsibility to marshal your data into a byte slice. And we'll talk about buckets more later, just for the fun of it. That's 4 and a 2. So it's a byte slice, and it gets displayed as hex if you don't ask for anything else. So we just put that value in, and we got it out, and it didn't change. Yeah, exactly. Woo, computers. Okay, one of the nice things about Bolt is that it is pure Go. There is no like C component that it is wrapping, it's pure Go. Which means that, for example, I cross-compile this thing for OS X and it just works out nicely. It also means that it understands things like garbage collection. You don't have to worry about freeing chunks of data. All of that is done by Go. And it's just a lot more pleasant API than in any of the key value store libraries that I've seen that have been wrapping a C library, because all of those need to live by the rules of the C library, and this thing gets to make its own rules. So it's inspired by a project called LMDB, Lightning database, and there's a CGO wrapper for it, so you can use it from Go. And it's kind of shares a lot of the underlying design, and right now they're starting to like go their separate ways. But the underlying design is completely, like, believably similar. So, kind of, in many ways, things that are said about LMDB apply to Bolt. So, for example, people say LMDB is good for this kind of a workload, Bolt is good for the same kind of workload. It's a library. So, what that means is that it's not something that you talk to over a network. It's not a Redis, it's not a Cassandra, it's not a MySQL. There is no network component. It is a library that uses a local file and does things for that one process that uses it. Now, you could write something on top of it if you wanted to, but that's kind of up to you, and it's usually better to provide more value than just that key value store. So it's meant to be used by a single process. So there is no concept of multiple things opening the database at the same time and cooperating. It belongs to a single process, and that's up to you to organize your application in a way that it makes sense. So here's a demo. When I say single process, technically it's a single owner, so we can have a single Go routine, have it open. But what we have here is a function that knows its own identity, and it tries to open the database, and it says when it succeeded, sleeps for a second, says that it's closing it, and then closes it. And we launch 5 of those that all compete for the database. And we see that 0 got it, 1 got it, 2 got it, 3 got it. And never you have 2 guys that have it open at the same time. So it really is a single owner database. And it's just a pure coincidence that they are in numerical order. It could be like 3 could get it first, 0 could get it next, so on. But that means that your application needs to kind of understand that this is the guy opening the file, and everything else goes through it. So a plain old key value store is not really all that useful always. A really useful property is to have an ordered key value store. And what that means is that whatever keys you put in, the byte order of them, you can go through the keys in that order. So in this case, what I'm doing is, and you would not use this in real code, this is like a dumb trick, I'm just printing enough zeros in front of the number so that it's always 4 digits long, so that it's 0001, 0002, which means that the bigger numbers sort the right way. And then I'm filling it with 100 numbers chosen from the range of 0 to 99999. And I put an empty value into each one of those, and then I walk through them in order. So what happens here is that we get a list of things that is literally a bunch of random keys in order. And they're in order because I put the zeros up front as padding. Otherwise, you know, if there were no zeros here, 1 would be before 5. But because it's 005, it goes before 401. So you need to kind of design your keys in a way that has the sort order you want out of the system. Okay. you can do things like go through a prefix. So what we're doing here is I'm assigning the 40 into prefix. I'm grabbing a cursor and I'm seeking to that prefix, or I could go past it. If there is no key beginning with those, I could end up at, 41. It goes to the first key that is possible beyond that point, or it could go to the end of the bucket. That is, there are no keys after 40, in which case the K would be nil and we'd exit. We'd exit the for loop. Anyway, we seek the prefix. As long as key is not nil, as long as we have keys to look at, we do this loop, and then at the end of the loop we always go to the next key. And if it doesn't have the prefix anymore, we went past the area we're interested in, and we should stop going through them. So this will, from that list of random keys, find the ones that begin with 40. And this is how you would do things like, you could organize your keys, for example, so that there's a user ID up front, and then things related to that user ID. For example, then messages, or a message thread ID, and then messages within that thread. And you could walk through the whole thread with that. And you can also do ranges. So what I'm doing here is I'm picking everything that is between these two numbers, and I'm once again seeking to the beginning. And now instead of a prefix compare, I'm doing a full-on byte compare. And as long as it is below my max key, I keep going. And once again, the marshal keys must kind of match the order you want them out in. So it's the NoSQL world where you model your data to match your queries instead of the other way around. And this will find everything between 4242 and 4730. So there are other keys that begin with 4s, but it doesn't show them because they're not in that range. And you kind of construct your application out of this. Now, how does it stay ordered? It has to use some sort of a data structure to keep the data in ordered form. So Bolt uses a B+ tree, and the thing to know about B trees is that they're kind of like binary trees that are grouped together so that it's more efficient to use with block devices. So to read from disk, to write to disk, they tend to have a good sort of logical grouping of keys. And that's the whole point of all the B tree variants. And then there's implementation details. So I call them B snowman trees because they're kind of all similar, and there's a funny thing in the middle. Sure. So one of the things that is often brought up at this point is LevelDB, which just about everyone has heard of these days. It's like Cassandras and whatnots, big tables, all of that is log structured merge trees, kind of familiarly called LevelDB. LevelDB is an implementation of that idea. So Bolt is not an LSM. LSM is something completely different. So let's talk about the difference between a B tree and an LSM. So when you write to an LSM, it appends to a log and keeps your new value in memory also. And once the log gets big enough, it sorts the in-memory thing and writes it out to disk, to a permanent file that is not mutated anymore. And if you delete something, it gets written over with a thing called a tombstone, so that it's dead now. But it's a delete is a write of a funny value. And these immutable files, slowly you pile up more and more of those. So what an LSM does is in the background it will combine multiple of those files together into a bigger immutable file and then delete the originals. So it will always like merge them together, and that's why it's a merge tree. Now, when you're writing, everything is good because all you need to do is append at the end of the log. Well, your typical write does a single sequential write, and it's all good. It's really fast for writes. The problem is that reads may need to look at multiple of these immutable files to find the actual key value that is actually up to date and the right thing to look at. So, an LSM is completely optimized for the idea of do everything you can to have sequential disk writes. A spinning disk which does like 200 seeks a second at most, is good for that sort of use, and it's completely aimed at that. And SSDs, like in this laptop, you still benefit from it, but the ratio of that benefit is smaller. So LSMs are completely aimed at that use case, and B trees are completely not. So that's kind of the way you can think of it is, with Bolt, you will have random writes around the disk as it needs to update the data, which on an SSD doesn't matter that much. But this is where the big difference between these two comes in. So an LSM is usually considered good for a write-heavy workload. If you have lots of writes and not that many reads. So for example, something like Cassandra that uses LSMs underneath is actually slower to read from than to write to, which is kind of a funny idea. Like most databases are faster to read than to write, but LSM is actually the opposite of that. And Bolt, then again, because of this and other things in its design, is really good for a read-heavy workload. So if you have something that is 50-50, you're kind of, I don't know. But if it is clearly 10% writes, 90% reads, Bolt usually wins. If it's even anywhere close to the other way around, LSMs usually win. Okay, that makes sense? Good. So just to give you an idea of like, what is a tool good for? Never choose because something is popular. Okay. A Bolt database has a single writer, as I mentioned earlier. So when a function f is updating the database, no one else is. Even within that single process. Only a single process can lock the database for itself, but even within that single process, a single function is running a write transaction, and nobody else gets to write to the database at that point in time. Now, that limits performance, but it's really easy to reason about. It's really easy to understand what's going on in the application. It has a property that's called serializable, which is just, it comes with a performance cost, but it comes with a great simplicity of thinking about the application. And it limits performance, but the limit is still pretty darn high. So we'll talk about that later. But this is kind of the single weakness of Bolt, maybe. It's not that significant. It's like complaining that your jet plane is too slow. Yeah, okay. Okay, so this is what it looks like to run a transaction. I define a little function here, and I'm using this funny syntax instead of defining it like a normal function, because when you do it like this, you can refer to variables that are outside this scope within the scope. So it inherits the surrounding scope. If you were to define the function on the top level, it would be really difficult to pass things into it. But now it's a closure that will just inherit everything from its surroundings. I don't think this example is using anything, but imagine the key and the value being variables that are defined somewhere outside here. Okay, so I just defined this function, and what it does is creates a bucket named bucket, and in that bucket we put this key with this value, and if something goes wrong in either one of these steps, we bail out with an error. If not, we return success, and this guy calls database update and passes the function to it. And if it returns an error, we do log fatal, which logs a message and crashes the application, like exit 1.
And what's a bucket? Is it that's the name of the transaction?
Bucket is a container of data, kind of similar to Amazon S3.
Oh, I see. Okay.
So, like, it's a key namespace.
I see. Okay.
We'll talk more about buckets a little bit later. There is also a thing called DB begin, which will hand you back a transaction object. But most of the times you really don't want to use it, because the good thing about this way of calling it is that you really can't forget to close the comment, close the transaction. If you return success, it will commit. If you return an error, it will roll back. And you don't have to manage that. You can't accidentally forget to do it. So it's actually really nice. Nice to use this for. So that was an update, which means it's a writing transaction, which means there can only be one at a time. There's also a read-only transaction, and the function we call is view, and everything else kind of looks similar, except for the difference that this guy cannot run any mutating operations. So this bucket is an open, like grab it for me. It does not create the bucket. If the bucket does not exist, this will return nil. So it's a read-only operation. Similar thing with get. If it doesn't exist, it will return nil, but it never writes data. And we can check whether the key existed or not, and we just print it out. And once again, at the end, you just call view with that function.